Look, mastering physics, it doesn't just happen by accident. It takes absolute precision, serious discipline, and a bulletproof strategy. You're gearing up for the 2026-27 board exams, and let's be real, you do not have time to waste on fluff. So this ICSE Masterclass Explainer is your definitive zero-distraction blueprint for the work, power, and energy chapter. I'm stepping in as your strict academic mentor today because my one and only goal is to get you that perfect score. We're stripping away all the noise and focusing purely on high-yield, objective board exam prep. Let's get right into it.
Here's exactly what we're tackling today: the physics of work, power, and the rate of work, energy forms and units, that all-important conservation of energy proof, your independent study checklist for left-out topics, and finally, your board exam action plan.
Okay, Module 1, the physics of work, moving beyond daily parlance.
To crush this section, you need to completely toss out your everyday understanding of the word work. Seriously. In daily life, sitting at your desk, studying, reading a heavy textbook, or even just thinking really hard, we call that work, right? But in the strict realm of physics, all that mental or physical exertion means absolutely nothing. Physics has a non-negotiable requirement. Work is only said to be done when a force applied on a body actually makes that body move. There has to be displacement. Think about it. If you stand in front of a massive stationary train and push it with literally all your might for a solid hour, but that train doesn't budge an inch, well, your physics work done is exactly zero. No displacement, no work. It's that simple.
Now, the mathematical reality of work is where you're actually going to secure those board marks. Work is the product of force, which we denote as F, and displacement, denoted by S. But here's the catch. The force you apply isn't always perfectly lined up with the exact direction the body moves. So the absolute definitive formula you have to burn into your memory is W equals F times S times cosine theta. That theta right there, that's simply the angle between the direction of your force and the direction of the displacement.
You need to lock these three special angle cases into your brain right now. Remember, work is a scalar quantity, meaning it only has magnitude, no direction. But that angle we just talked about, it totally dictates whether the work done is positive, zero, or negative. So if you push an object and it moves in that exact same direction, the angle is 0 degrees. Cosine of 0 is 1, meaning your work is positive. Now what if you're carrying a heavy load horizontally? Your force against gravity is pointing straight up, but you're walking forward. That makes a 90-degree angle. Cosine 90 is 0, which means, crazy as it sounds, the work done against gravity is actually 0. And finally, if you throw a ball straight up, gravity is pulling it down while it moves up. That's a 180-degree angle, making cosine -1, which results in negative work.
Okay, let's talk units. The SI unit of work is the Joule, and the CGS unit is the Erg. And let me tell you, board examiners absolutely love testing your ability to convert between the two. So I want you to memorize this number right now. 10 million. 1 joule is strictly equal to 10 to the power of 7 ergs, period. Don't second guess this on exam day, just know it cold.
Moving right along to Section 2, power, rate of work. We're looking at speed and efficiency in mechanics.
Because look, actually doing the work, that's really only half the battle. The time it takes you to do it is what separates the top scorers from everyone else. By precise definition, power is the rate of doing work. It depends entirely on just two factors: the amount of work done by the source and the time taken to actually complete it. Think of it this way. If you do the exact same amount of work as the person sitting next to you, but you get it done in half the time, your power is literally double theirs. And for the record, the SI unit for this rate is the watt, where 1 watt equals 1 joule of work done in exactly 1 second. Now, you're probably already familiar with the primary formula: power equals work divided by time. But here's an insider tip. Board examiners are actively hunting for students who understand the deeper mechanics. So you absolutely must memorize the alternate formula as well. Power equals force multiplied by average velocity. That's P equals F times V. When a constant force is moving a body at a steady speed, this specialized little formula is exactly your secret weapon to solving those high-level numericals in record time.
Before we wrap up power, there's one more highly tested number you have to commit to memory: 746. In the world of mechanical engineering, power is constantly measured in horsepower, and 1 horsepower is equal to exactly 746 watts. So when a tricky numerical question asks you to convert your final answer into horsepower, you just take your total watts and divide by 746. Write that down right now.
All right, Section 3, energy, forms, and units. The literal capacity to do work.
So if work is the action itself, energy is the fundamental requirement you need to actually perform that action. They are so intimately linked that they share the exact same SI unit, the Joule. But while the Joule is your standard, you're going to encounter scenarios on the exam that require entirely different scales. For instance, 1 watt-hour is 3,600 joules. But the really big one to watch out for is the kilowatt-hour, which equals 3.6 times 10 to the power of 6 joules. This is the commercial unit. It is literally the exact metric the electricity meter outside your house uses to measure your power consumption. Scaling down, 1 calorie equals 4.18 joules for heat energy. And way down on the microscopic scale, like for atomic particle acceleration, we use the electron volt. That's a microscopic 1.6 times 10 to the power of negative 19 joules.
Now, mechanical energy exists in 2 primary states, and you need to know the difference. First up is kinetic energy. This is the energy a body possesses simply due to its state of motion. A speeding bullet, a rolling boulder, they have kinetic energy, which you calculate as 1/2 mass times velocity squared, or half mv squared. The second state is potential energy. This is the energy a body has when it's at rest, strictly due to its position or its shape. Think of a tightly compressed spring or a heavy rock perched right on the edge of a cliff. For gravitational potential energy, your go-to formula is mass times gravity times height, or simply mgh.
Let's jump to Section 4, Conservation of Energy Proof. This is the centerpiece derivation. Okay, I need your absolute, unbroken focus right now. Put the distractions away. This is arguably the most critical theoretical proof you are going to face on your board paper. The law of conservation of energy states that energy is neither created nor destroyed, it's only transformed. Let's actually prove this using a freely falling body. Imagine an object dropped from a height. At the very top, let's call it point A, its initial velocity is exactly 0. Because it's not moving yet, kinetic energy is 0, but potential energy is at its absolute maximum, mgh. So total energy equals mgh. Now, as it falls down to point B, covering a distance we'll call x, it gains speed. Its kinetic energy increases to mgx, while its potential energy drops to mg times the remaining height. If you add those two together, the x's mathematically cancel out, leaving the total energy perfectly at mgh. Finally, right before it slams into the ground at point C, the height is 0, so potential energy completely vanishes. Every drop of that initial potential energy has converted flawlessly into kinetic energy, which is now mgh. The total mechanical energy didn't change once. It remains entirely constant. Boom, we just ruthlessly proven the law.
Section 5. Left out chapter topics. This is your knowledge gap checklist.
Look, as your mentor, it's my job to give it to you straight. This explainer is a high-yield, purely tactical masterclass, but it absolutely does not replace your own independent grinding. I deliberately omitted certain topics today, and you must conquer them on your own to completely close the gap on your syllabus. First, you need to independently study the exhaustive commercial energy transformations. You have to understand exactly how a dynamo differs from a motor. Second, you need to practice step-by-step numerical problem solving. Don't skip that. Third, you've got to write out the detailed linear momentum and kinetic energy relation derivations yourself. And finally, make absolutely sure you can thoroughly prove the work energy theorem from start to finish. That's on you. Which brings us to Section 6, your board exam action plan. These are your mandatory final steps.
We've covered the core concepts, but frankly, your real work is just beginning. Watching this explainer was literally only step 1. So here is your authoritative directive. Check the bio and description below this explainer right now. Inside, you're going to find direct links to download the official ICSE Masterclass Premium Study Notes and our complete formula sheets. You also need to visit the ICSE Masterclass website and join our Telegram channel so you can grab the required question bank. I know the standard we are setting here is incredibly high, but I also know you have the potential energy inside you to achieve a flawless score. All the tools you need to absolutely dominate the 2026-27 board exams have been laid out right in front of you. The only question left is, are you ready to convert that potential into kinetic energy and put in the actual work?